Morning, everyone, or afternoon where you're at. Sorry, I'm not going to be there today. Our furnace stopped working last night, so I'm waiting here to try and meet the repair guy. Hopefully, he can get it done. So it's 5 o'clock in the morning where I am at, sitting by the fire in our basement with the space heater. So we'll go through this. If you have any questions, just see me tomorrow morning. Hopefully, everything will be squared away and I can get into the intervention day on Tuesday. This topic, well, obviously you're going to need to know it. It'll be on the test. Is not what we're going to be quizzing on. We have a little quiz on Wednesday, but it's the next section that we'll be quizzing on. So if there are any questions on this, you'll have some time to ask. So you'll see here, this says number one. I guess we can talk about it first of all. It's called partial fractions is the method that this is dealing with. So obviously you can kind of see if we look through all the problems here, you're looking at fractions. So number one, if I ask you to add those two fractions together, what you would know how to do from old algebra ideas is in order to add these two fractions together, you have to have a least common denominator. And when you're dealing with a rational function, more times than not, your common denominator is just going to end up being the product of those two expressions. Then what we would know is in order for us to then now be able to add these, they each have to have that denominator. So this first one would need an x plus a 7. So as long as we multiply both top and bottom by that, we're really just multiplying by 1. This one is missing the x minus a 4. So if we multiply again, x minus 4 over x minus 4, we're really just multiplying by 1. So if we now go through that step, what you're going to end up with is 2x plus 14. That's just distributing these plus a 5x minus 20. So these guys multiply together. That then is going to equal a 7x minus a 6. And then our common denominator now is the product of those two. And in regards to step number one, me just wanting you to add those two fractions together, you would be done. We review that, so then if I ask you to do number two and reverse it, we at least sort of remember how we would have done the initial step. So now, if you notice, what we ended up by multiplying those two fractions together is we ended up with this 7x minus 6, and then over what we said our common denominator should end up being. So long term, what's going to happen is this is actually the step you're going to be starting at. And if I throw an integral in front of this, the way that looks with a fraction is a problem. Like products, fractions, we have to do some sort of a substitution with. So this is going to be a really common method when you substitution doesn't work and you have a fraction, more times than not, it's going to be this partial fractions idea. So now what I want you to do is reverse this. So that if I gave you this, how could we actually figure out what these two original fractions up here were? We obviously know in this case what they are, but in the problems we're going to do here in a minute, we won't. So what we should find when we go through this process we're going to go through right now, initially we wouldn't have known what the a is. When we do all of this work, we know a better end up being a 2. If we don't know what b is, and we go through all of this work, if we look up to number 1, we know in this case b better end up being a 5. Because if I ask you to integrate this part of it, that's a problem. But if we can rewrite it like these, and I ask you to do the antiderivative, these two fractions then we can handle. So that's our goal, is to try to figure out a process that would allow us to go from this version to the version that we started with. And it's pretty darn similar to what we just did. Identify what your least common denominator is. It's this x minus 4 times an x plus a 7. So this one needs to get multiplied by that x plus 7 over x plus 7. This one would get multiplied by the x minus 4 over x minus a 4. So if we do that, this product here would give us ax plus 7a. And then this product here would be bx minus 4b. And then all of that now has a common denominator, which is good. It's our goal. The next step, then what we want to identify or look at, notice how we now have an equation. So that's how this is going to play out in general. So as we go to clean this up, we have, what I'm going to have you do is just talk about how, because of this, now that we have an equation, let's just say we multiply everything by your denominator right now, so that when we do that, this would cancel and this would cancel, and all we're really left with now is this 7x minus a 6, the original numerator, and then what this numerator has turned into is this. So then we're going to set that equal to the ax plus 7a plus bx minus 4b. Next step. Notice how we have some like terms here. We have an x here, and we have an x there. So I'm just going to rearrange those so that those are consecutive terms. And then the non-variable terms, the 7a and the negative 4b, we're going to arrange those so they're consecutive. Next step, take these two, pull out that common factor of x. And when we do that common factor of x, place that behind, just so it's going to look, the visual is going to be better here in a second when we do the problem. Okay, and then the next one, sorry, I was trying to figure out how I screwed this up. This should be a 7a. Fix that. Then from there, sorry, it was a long night, up early. So that should be good now. And then just group those, put those in the parentheses, the non-variable terms. The reason this is now important is what this is going to allow us to do is, since these are set equal to each other, notice how I have an x term right here, and the coefficient of x on the right-hand side is a plus b. I have a coefficient of x on the left-hand side, which is 7. What that would then tell us is what has to be true is that 7 must be equivalent to the sum of a and b. Similarly, with your constants, notice how these are our non-variable terms. So these are our constants on the right-hand side. Here's our constant on the left-hand side. So we can also set those expressions equal to each other. Then what you are now looking at, we can't solve either one of them individually, but what's going to happen in every single one of these problems is you have this little system of equations. So if you like systems of equations, hopefully you remember how to do them. If not, you'll catch on pretty quickly, I would hope, because we do it for every one of these problems. You can do elimination, you can do substitution. It's really up to you. Substitution isn't too bad right here. If you want to solve one of these for a and b, doesn't matter. I'm partial to elimination when given the opportunity here. So I'm going to multiply by everything by a 4. So 4 times 7 would be 28. 4 times a would be 4a. And then the 4 times the b would be a positive 4b. Yeah, I really am tired, aren't I? Sorry, I keep screwing this up. I don't know why. I'm having a hard time with that one. So this should be our 7a. So I took the negative 6 here. We have that. Should be 7a minus 4b. All right. So then, now that we've distributed the 4 to get 28, 4a, 4b, now we're going to go ahead and add these to get rid of the b's. So this would give me a 22. This would give me 11a. These guys are going to cancel. Notice how a equals a 2. So if we revisit, now that this has moved, notice how a was over the x minus a 4. That's what we knew our 2 was supposed to be. And then since we know the sum of a and b has to equal 7, pretty quickly we can identify that our b is 5, just like it was supposed to be in this original problem. So what that now allows us to do is to take this problem here. So let me redirect a little bit further down. And now we can write this as, instead of a over x minus a 4, we know that that was 2 over x minus a 4. Instead of this b over x plus 7, we now know that's 5 over x plus 7. That's what we want the antiderivative of. Again, this we can't do the way this is currently written, but now that we have this, remember how we can take this 2, just put it out in front. All you're really dealing with here is a couple of natural logs. So this would be 2 natural log of x minus a 4. This would be 5 natural log of x plus 7. Add your constant. This is the antiderivative of that. Okay? That's the partial fractions method. So every time, it's more algebra than calculus, to be quite honest. Really, just the very last step here, where you're going to be doing the antiderivative, is something calculus related. Everything else before that is just some algebra. Couple things to look at then. The main thing I want to just point out is that numbers 1 and 2, the degree in your numerator for this to work must be less than the degree in your denominator. If it's not, then this method just simply isn't going to work. Number 2, we want to separate these into linear factors. That's what we're going to make sure of. So we have to have linear factors down here. So the degree of our x's have to be 1s. And then I'm going to have you add one more thing here. It probably should go right here now that I look at this. You cannot have repeating factors. What that means is if we ever set this up, notice how the factors here are x minus 1, x plus 2. If we have a repeating factor down here, once again, this fraction won't work, or this method won't work. So with that, let's jump in. Let's try number 1 right here. And I think usually we do 1 or 2, and then most people are pretty well squared away with this. So for number 1, what we're looking at right now, we don't know the antiderivative of this. It's not something we can just look at and then know. So what we're going to do is separate these into 2 separate factors. 1 over the denominator of x minus 1, 1 over the denominator of x plus 2. This we will hopefully be able to integrate once we know what a is and once we know what b is. So that's kind of this process now. How can we figure out what those are? So the way we're going to set this up is we're going to find a common denominator. So I'm going to rewrite the left-hand side. Our least common denominator for this one is just the product of those 2 fractions. So what we're going to do is multiply this a term, this first fraction, by the x plus 2. So we do a times x plus 2. The b term is missing the x minus 1. So we're going to multiply that by x minus 1. Now we'd say we have a common denominator. Moving forward, this will probably be the last time I show the denominator, because then what we're going to ultimately kind of say in this next step is every single time we would just multiply this fraction by, since it's now an equation, we can do this common denominator, and it would cancel this out, it would cancel this out, it would cancel this out. So moving forward, we're really not even going to show this step anymore, at least not the denominator part. And we're going to jump right to, if I can erase all of these, this step right here. Okay. Now we can go ahead and start to kind of set up the system. So what we're going to have is the 8x plus 1 must be equal to, we're going to distribute here, ax plus 2a plus bx minus ab. Let's group these, or write the common like terms in consecutive order. So put the ax plus the bx, and then the 2a minus the b. From there, factor out the common factor of x for the first one. And then, well, you don't necessarily need to group these. I like putting them in parentheses so we know that then the 2a minus the b has to equal the constant on the left side. So what we would then know is that 8 has to equal a plus b. And we're just getting that. Here's x. Here's x. So if the coefficient on the left-hand side is 8, the coefficient on the right-hand side is a plus b. Those have to be equivalent to each other. Our constants then, the constant on the left-hand side is 1. Constant on the right-hand side is that 2a minus b. This one we can add right away, if I do it right, because those b's will cancel. I get 9 is equal to 3a. A equals 3. From there, what we then know, if I use this equation right here, is that a plus b needed to equal 8. So then pretty quickly we know that our b has to equal 5. So what that now allows us to do, again, let me just come on over here, is that we can now say that a was 3 over x minus 1, and then b, which was 5 over x plus a 2. Those we can now handle. Now we finally do a little calculus. 3 natural log of x minus 1 plus 5 natural log of x plus 2 plus your constant. That's our antiderivative. Okay. I'm going to do one more before I do number 2. 2 is the one that you want to be careful of. It's really the only one that's somewhat of an issue. So jump to number 3, and then we'll come back to number 2. How number 3 is a little bit different, if you notice this, it's not factored. So what you just want to understand, a lot of people when we first look at these would think u substitution, and that's still a valid thought. We don't want to forget about that. And most people would think let u be your denominator if we just consider our exponents. But then when we take our derivative, while we do get an x to the first like we're supposed to in the upper limit, it's just not going to match what we needed because we get a 2x minus a 2. There's really not much we can do to make a 2x minus 2 equivalent to this 5x minus a 3. So we would then realize, okay, u substitution doesn't work. If it's a fraction, more than likely, then it takes us to this current method of a partial fraction. So what we would just want to do is go ahead and set up an a and a b, but as we do that, we're going to want to factor that denominator. So when we factor this denominator, we're going to get x minus 3, x plus 1. And then we just now need to kind of figure out what a is and then what b is. Least common denominator, we hopefully now can realize is x minus 3, x plus 1. So I'm going to do this over here. So we do 5x minus 3. This has to get multiplied by the x plus a 1. So a times x plus 1 would just be ax plus a. And then bx minus 3b. Write the x terms in consecutive order. Write the non-x terms in consecutive order. Probably last time well, not necessarily. I do like kind of showing that we're factoring this out, but if you can skip this step, certainly understandable. So from here, 5 now has to equal a plus b. The negative 3 has to equal a minus 3b. Now, if you notice, we can get rid of those a's if we subtract. So I'm going to subtract those two equations. We get 8 equals 4b. So we now have b equaling a 2. A plus b equaled 5. So our a would need to equal 3. What that then allows us to do, let's go back up to the top of this problem. Instead of a over x minus 3, we now know that's 3 over x minus a 3. Instead of b over x plus a 1, we now know that's 2 over x plus 1. Okay. Both of those pretty straightforward. 3 ln x minus a 3 plus 2 natural log absolute value of x plus 1, and then plus your constant. Okay. So hopefully at this point you're kind of catching on a little bit. Pop up here to number 2. I assure you, this is the one you would get on the AP test. I will certainly expose this one to you now, but also on our test. This is the one you just want to be somewhat careful with. Starts out the same, where we're going to go ahead, say that equals a. This one's already factored for us, so we don't have to worry about that. And then we'll put the b over the other factor. And then now just go through your steps to figure out what your a and your b are. Usually we've done this 3 times. People can do that. So if you want to start cranking that out, feel free. And I'll do it down here. So we should know now our x plus 18 would equal, I'm going to start kind of combining some steps here. We have ax plus a 4a, and then 3bx plus 5b. We just multiply the a and the b by the missing term in the denominator, or what should be our common denominator. This is the step. If you don't want to write these and just factor them right away, feel free, but I do like showing them in the order. And then in this next step is when I factor them out. So we get a plus 3b. That's our coefficient for the x on the right-hand side. And then the 4a plus 5b is our constants on the right-hand side. So in this case, 1 has to equal a plus 3b. 18 is going to equal the 4a plus 5b. Solve that system however you prefer to solve a system. I'm going to multiply this one by a 4 so I can get rid of the a's. Oh, running out of room here. So I'm going to do this over here. So I'm going to get 4 equals 4a plus 12b. And then this one I'll just recopy. 18 equals 4a plus 5b. To get rid of our a's, we need to subtract. So we're going to subtract. So b negative 14 equals 7b. And then we can see that our b is a negative 2. Once we know b is a negative 2, which one will we plug it into? I'm plugging it into this one here. A plus 3b is a 1. We now know b is a negative 2. So what does that mean? Negative 6. A is a 7. So what we're then going to do, come up to here. We now know that this is 7 over 3x plus 5 minus 2 over x plus 4. That's what we want the antiderivative of. So far, this model is the exact same process as our first 3 problems. But now as you look at this, here's where you want to be really, really careful with doing this. I'm going to create a little space down here. So let me erase these guys. We know what these are. Here's what we now want to be careful of. So if I go back to number 3, if what we've talked about, and you hopefully understand, I think we do all understand, the antiderivative of this gives us this equation right here, that function. I should now be able to take the derivative of this. And when I take the derivative, I better end up with what I started with. So if I do that, I'm going to do 3. The derivative of a natural log is 1 over x minus 3 times a 1 plus the 2, and then times 1 over x plus 1. Derivative of x plus 1 is a 1. So notice how this will give us 3 over x minus 3. That's good. That's what this was. This one would give us 2 over x plus 1. That's also good because that's what we started with. Well, if we go now to this problem, if I do this antiderivative, like I'm going to guess most of us would do, you're going to do 7 natural log of 3x plus 5 minus 2 natural log of x plus 4. You're going to be feeling good about yourselves, and you're going to think that that is our answer. But this is why we want to be careful. If I now take the derivative of this, I better end up with what we started with. So I'm going to drop the 7. The derivative of a natural log is 1 over 3x plus 5. But now the derivative of this inside gives us a 3. Here, 2, and then the derivative of a natural log is 1 over x plus 4. Notice how this derivative is just a 1. So what we really end up with here, what we're about to end up with here is, notice how we have this 7 and the 3. Those multiplied together are going to give us a 21, not the 7 that it's supposed to. Second one's good though, right? Like if I do 2 times this 1, that's going to give us this 1. So as long as your denominator here has a derivative of 1, we can do the same thing that we've been doing for the first 3 problems that we can here. Everything's going to work out with this one because we get this 2 over x plus 4 like we're supposed to. But clearly, this doesn't work because this 21 isn't the 7 that we're supposed to get. So what you want to understand then, if the composite doesn't have a derivative of 1, so this guy right here, which ultimately is your denominator, what this really is, in this original setup of this original problem, it's actually a little u substitution problem. Now, you don't necessarily have to do u substitution all the time. If we understand how that played out and now how u substitution is going to work, that 3x plus 5 is your u, du is 3 dx. Well, notice how we don't have that 3. What you want to do is just divide this over so that we get 1/3 du. So the way this problem really would get done, remember how we talked about we may have to separate integrals a little bit more? I'm going to create 2 different integrals for this. This is now going to get done using u substitution. So what I'm going to do is pull the 7 out. I've just found that my denominator is my u, right? But then through the process to get rid of ultimately our dx, what dx is equal to in this first part of the integral is a 1/3 du. So what that then gives us is 7/3 for this one times that natural log of u. And then this one, let me just rewrite it, this step. But then we'll go ahead and do that antiderivative. This plays out normally. Okay. That then is going to be our answer. If we took the derivative of this, now we're going to be good. Actually, let's plug in what u was at the beginning. And then this guy is going to stay the same. So, do we need to do u substitution every time? No. I would propose you don't want to do u substitution every time, but we do have to understand whatever this coefficient is. It's kind of like with trig functions, so it's a3. What we have to do to make sure this is going to play out correctly is whatever that coefficient is, when we do our antiderivative, we then have to take that coefficient and divide it by 3. And if you can keep that straight, if you understand that, that's really the only thing that can trip you up with these. Okay? Hopefully that makes some sense. If not, that's something that I'll try and explain in further detail if you want to drop in one day to second period or the MRC. All right, real quick. These last few, these are now ones that have little tricks. I don't think we'll do number 5. Well, we'll go through. We'll figure it out. Number 4. So this starts out the same. We're going to factor this. We're going to say x minus 5, x minus 1. We have our a and our b. So the only difference now, notice how you just have a 4. That's the only little curveball. But everything else kind of plays out normally. So the a has to get multiplied by x minus 1. The b is going to get multiplied by x minus 5. Then from there, I'm going to break my rule to spare you guys having to listen to too much of this on a video. And most of us are fine with this step anyway. So it's at this step where things are just a little bit different, because now as we look, here's my x, and the coefficient of x on the right-hand side is a plus b. But if we look on the right or left-hand side, notice how there is no x. So that would just simply mean, if we wanted to show that there was an x there, that the coefficient of x on the left-hand side is a 0. So you're going to set that a plus b equal to 0 because we didn't have an x there. Constant's the same. Just let 4 equal the negative a minus the 5b. Add, and what we find pretty quickly is that our b is a negative 1. Since the sum of a and b is 0, that tells us that a must be positive 1. So come up here, let a be 1. Let your b be the negative 1. No tricks here. The coefficient of both of these denominators are 1. So what we just talked about from that previous problem number 2, we don't have to worry about dividing or anything. We're ready to go ahead and do our antiderivative. And then that's our answer. I will point out, I'll do it since this is a nice quick one. You will find sometimes multiple choice wise, this is going to get simplified. So what that then sometimes entails is we would write this as 1 natural log. If you recall, if we subtract natural logs, we could write them as 1 if we write their composites as a fraction. Okay? So that's that one. Number 5. The reason this one is an issue, we won't go all the way through it maybe. Maybe I'll just show you kind of the setup of this, and I think you'll get the hang of what would need to be done, is that the rule that we have written up here, the degree of your numerator must be 1 less than the degree of your denominator. If we go to number 5, we'll see that that's not the case. The degree of our numerator is 1 larger than the degree of our denominator. So that may mean we just can't do it altogether. But you can see I left a lot of space for this, so this can be done. So this is kind of one of these little tricks that we want to make sure that in due time you might see. And that is, in order for us to make this guy work, most people really love this when I show them this, is what we actually want to do is some long division here. So if you recall, remember how you did long division, where you're going to take your denominator and you legitimately, like old school style, divide this into the numerator. So when we did that, or when you would have done that in your life, you would have taken this first term, divided by the first term here. So if I did the first term of 2x cubed and I divide it by x squared, this would give me just a 2x. So that's what I would get there. Then we take that, multiply, so 2x times x squared, 2x cubed, 2x times a negative 4, or negative 2x is a negative 4x squared, 2x times a negative 3 is a negative 6x. Then you would know we got to subtract these. Well, not only does this cancel, which it's supposed to, but these second terms are also going to cancel. So that's nice. It's going to make this somewhat less of a pain in the butt. And what we are left with now is a 5x minus a 3. The reason that is nice is now what you're supposed to do is take this term and divide it by this term. Well, now notice how this degree is a 1, and what we're going to be dividing it by is something with a degree of 2. So what that's going to have us do now, we're going to rewrite this as, this went in nicely as a 2x. But what this now is really our remainder, right? Because now this here is smaller than this term here. So it's kind of like a fraction when you would do long division the old way. Once your denominator is bigger than your numerator, that's your remainder. Then you're kind of done with that long division process. So what we're then going to do is to take our remainder, and this is what we would do in long division anyway, and divide it by the original divisor. And if you now notice, this we can do, right? This is x squared. This is now a partial fractions problem. However, actually can't stop there because I believe, if I remember correctly, isn't that number 3? So now if I take number 3, you would just go through this process to evaluate this, and then you would just add that on to this original antiderivative from 2x. I'll spare you that, but basically what I'm just saying is now this turns into its own problem, and we would just go through with our partial fractions method that way, okay? All right, last one. Last thing that could happen is that when we go to factor this guy, let me actually start you factoring here. When we pull out the common factor, it's always kind of your first idea when you factor. Notice how when I pull that 2x, we unfortunately get a difference of squares, which factors further. So usually at this point, we're at the end of the period, and I don't have to watch your faces right now, and you'll be all watching this at the same time. When I show this, there's just collective moan and long look on everybody's faces. So I'm just going to imagine that in my head, everybody doing that right now, because most people are understanding this pretty well. So they then understand what this is going to require us to do is not just have an A plus a B, but also a C for all 3 of these factors. Okay? So if you want to moan, if you want to say something bad about me in your head right now, now is that time. But this is what we need to be able to now work through in this problem. Okay? So let me get rid of all of these so I have some room to operate. So on the left-hand side, we now need to go ahead and do the same thing we've been doing, but we're going to do this with 3 terms. Keep in mind, I'm going to rewrite this now. Your least common denominator is the product of all 3 of those guys. The 2x, x minus 2, x plus 2. So what the 2x is missing, what we would need to multiply that by is this. So let's make this somewhat manageable. If I'm multiplying by x minus 2, x plus 2, aren't I really multiplying that a by an x squared minus a 4 if we multiply these together as a difference of squares? So that would give us ax squared minus 4a. The b then, so let's go to our b. What the b would have to get multiplied, notice how it's missing the 2x and the x plus 2. So that's the 2 terms that it's missing. So be smart about that. Now, what b is going to get multiplied by is 2x times x plus 2. So that would be, what, 2x squared plus 4x. So that's going to give us 2bx squared plus 4bx. Erase those. And then last but not least, The c is missing 2x and x minus a2. So we're going to multiply that by the product of these two. So 2x squared minus 4x. So that would give us 2cx squared minus 4cx. Okay. So then from there, if I get my eraser to work, let me get rid of that. No need to have that integral there just yet. Go ahead and let's group all of these together. So I'm going to take my squared term. So here's the squareds. I'm going to go ahead and factor this out. So the x squared factored out would leave us an a for our first term, a positive 2b for the second term, and then a positive 2c for the third term. If we go to our x terms, so here and here, so when I go to write this one, we just have two of those. So when I pull that out, you'd have a 4b for the first one and a minus 4c for the second one. And then last but not least, notice how we just have this one constant right here. So that's plus a negative 4a. So from there, the x term, square term on the right, notice how there isn't one over here. So that would then just mean that the a plus 2b plus 2c is equal to 0. We do, however, have an x to the first term over here. That's a 1. So the 1 must equal 4b minus 4c. And then last but not least, the 3 has to equal a negative 4a. So if you notice, we have three different variables. So it's a system of three variables. But it does work out nicely in the sense that we can get a right away to be a negative 3/4. And since a is now a negative 3/4, what I'm going to do is come up here, let a be the negative 3/4. So you're going to get 0 equals a negative 3/4 plus 2b plus 2c. And then right away, I'm going to move that 3/4 over. So let's now, I'm going to erase it. I'm running out of room a little bit. So I'm going to add that 3/4 over. And then, see, that's why it's nice to have everybody in class so I can see some strange looks. This should have been a plus 2b plus 2c. I forgot the 2c. So let me rewrite that right there. Which then means we have a 2c over here as well. So if you did the same thing, you just were copying me because I'm going too fast, and you have that. I'll give you a second to correct that. And then now what I'm saying is I'm going to take this 3/4, I'm just going to add that over so I can conserve some space. So I'm going to get a positive 3/4 on the left-hand side of this equation. And then I'm going to line that up with, I'm just going to take this guy, so I'm just rewriting this with the 3/4. This is 4b minus 4c. Up to you what you want to do now. You may want to get rid of the fractions. You may want to multiply to get rid of your b's right now. It really is up to you. I'm going to multiply this top by 2. So if I do that, what I'm going to get is 6/4. So 2 times 3 is our 6 over 4. 6/4 is 3/2. And then the 2 times 2b is 4b. The 2 times 2c is 4c. So then that's going to allow me to, let's see here. That should be plus 4c, yeah. So I'll just distribute here. Yeah. So then what I'm going to do is add. So this will give me 5/2 equals 8b, and then these guys would cancel. So then we now have b to be 5/16. So we have a, we have b, and then mercifully, all we need now is c. So I'm going to get c using this equation, okay? So 1 equals 4 times b, which we now know is 5/16, minus our 4c. So what's that? 20/16, so that's 5/4 minus 4c. I'm going to add the 4c over, so it becomes a positive 4c, subtract 1, gives me 1/4, and then that's 1/16. Finally. So now let's go up. We're still not done, right? This is fun. Because now we have to come up here and set this up. So the way I'm going to set this up, actually, I'm going to come right here. I'm going to erase the a. So I'm going to show you something. We now know a is the -3/4. We now know that our b was what's... Okay. 5/16. And our c, we got to be 1/16. So when we now go to do this, understand sort of that first one in particular, pull this guy out with the -3/4. So if I did a -3/4 divided by 2, that's a -3/8. So that's our coefficient that we're just going to have in front of that integral. And then all we would be doing the antiderivative of really is that x. So it's just -3/8, the natural log of x. The others are pretty straightforward. This is 5/16, the natural log of x minus a 2. And then 1/16, the natural log of x plus 2. And then plus our constant. And then voila, that's our guy. All right. So with that, that's all I have. Again, sorry I'm not there. Hopefully this makes some sense. If you need clarification about anything, you're obviously more than welcome to drop in a second period. This stuff isn't on your quiz, so you do have a little bit of time before this is something that you would need to reproduce on some sort of an assessment. All right. Hope everybody's having a good day. We will see you tomorrow.